So thank you for joining our webinar. My name is Lee Hong. I am the Director of R&D Biomolecules here at Biotage, formerly PhyNexus. I've been with PhyNexus since 2006, so this is essentially my first job. My colleagues have joined me today as well. Sean, he is a Regional Marketing Manager, and then Shadi is here as well. So Shadi, do you want to introduce yourself?
Yeah, I am the application scientist. I support the East Coast. So for some of you, that would be me helping you install the system and supporting you. And I am doing a kind of live-ish demo later in the webinar. So if you guys have any questions on that, I'll be able to answer it.
Great. So feel free to use the chat function to ask questions. Shadi will be able to answer them as he goes. Otherwise, he'll interrupt me, and then I can answer them as well. And then at the end, we'll open everybody up your microphones so we can have a discussion. Okay. So what do you think, Shadi? Should we just jump right in?
Yep.
Okay. Okay. I'm going to share my screen now. Great. Okay. Okay, Shadi, can you see the screen?
Yep.
Great. Okay, so thanks for joining the webinar. Thanks again. This is a presentation on our PhyNexus PhyPrep Maxi system. Like I said, PhyNexus is based in San Jose, and we were acquired by Biotage about 2 years ago. Biotage is a global company based out of Uppsala in Sweden, and we have research sites in Salem, in Cardiff, in Lund, and we have business sites around the world. And so we're happy to be a part of Biotage. Biotage are experts in separations, and PhyNexus is bringing the biomolecule separation to their portfolio. And so now we have a bigger reach. If you known us as PhyNexus, you know what our capabilities of, and now with Biotage, we'll be able to have even more support. Great. So for this presentation, we're going to talk about kind of how we see the plasmid DNA purification market and the need to automate plasmid preps, especially on the larger scale, the Maxiprep scale. I'll introduce you to the core of our technology, which we call dual flow chromatography. Then I'll introduce our Maxiprep kit, and then follow that with the demonstration by Shadi. So he'll be actually showing the system, how everything runs. But because of COVID right now, we decided to do some social distancing, and he was able to record this. So we'll be playing that recording for you. Okay. So this is really our view of where things were a few years ago. As PhyNexus, before we were acquired, we had established ourselves as a small volume purification company for life sciences. And a lot of what we did was purification of antibodies, especially for biopharma companies looking to screen antibodies for leads and to generate those leads and mature them into potential drugs. And as far as we were concerned, antibodies came from hybridomas, taking the mouse, immunizing it, and then sacrificing it to take the spleen cells to fuse with myeloma cells to create hybridomas, and then get antibodies, which would then be purified by PhyTep columns packed with Pro Plus resin, Protein A resin, Protein G resin, et cetera. And as we visit our customers and we talked, we would hear conversations in the hallways, people really bummed out about, oh, today I have to rerun 8 Maxipreps. And so it kind of, these things, we kind of recorded them as interesting little tidbits. And then our customers started to tell us, actually, you're a little bit wrong. Most of our antibodies are not coming from hybridomas. We're shifting gears and using transient transfection. And so that really got us interested about kind of trying to keep up with what pharma's doing, trying to make sure that we're relevant. So we started to study up, and we found that transient transfection is great because now we have the ability to, or companies have the ability to do really rational drug design, really do libraries and do a lot of mutagenesis to create libraries of antibodies that can be screened. And we found that the advantage of transient transfection as a way to generate antibodies was with the ability to really get full post-translational modifications. And we found that people were using different cell lines to get very high density, efficient production of mammalian proteins. The media that were being used now were developed without having to supplement with serum. And people were using different uh, higher quality transient transfection reagents to really increase the ability to get the plasmids into the cells. And as we were walking the hallways and we hear people being bummed out about doing Maxipreps, we wondered, well, what the issue is. And what the issue is that there's actually a high requirement of the amount of plasmid that is needed for transient transfection. So kind of the way that we see it is, in a nutshell, if you have 1 milligram of plasmid, you can do a 1 liter expression and you can generate 1 gram of antibody. And that is a pretty large amount of antibody, that's a large amount of plasmid than what we were used to, growing up in the molecular biology field. We typically just did Kaizen mini preps and got a few, micrograms or so. And so this was a scale up, and there was been a lot of adoption of Kaizen kits for the Maxiprep, for example, that were quite labor intensive and manual. And so we decided to look at that and think, okay, well, what can the PhyNexus technology do? Are there any bottlenecks that we can alleviate here? So we kind of analyzed what is it about a Maxiprep purification that is automatable, and what are the challenges? And so from just a very simplistic view, when we are looking at a Kaizen Maxiprep kit, typically the researcher would pellet cells, decant them, resuspend, lyse, and neutralize. Then the sample is cleared. The clarified supernatant is applied to a column, and we notice that the column is rather high in back pressure. Wash is typically done under vacuum, followed by a gravity elution, and then there was typically an ethanol precipitation and a resuspension step at the end. And so if we look at this, automation isn't simply taking a manual method and automating it. There are key steps that are just not friendly to automation. And so if we wanted to look at this process, if we wanted to develop a kit or a solution that can automate plasmid DNA preps at the Maxi scale, we're going to have to address 3 key features that we knew would be a challenge. That is, first, clarifying that supernatant, because centrifugation and syringe filters are just not amenable to automation. High back pressure columns, we know, are difficult to deal with, and especially when samples can be variable. The E. coli cultures can be high density, they can be overgrown. There can be a lot of variability that causes variability in how the sample interacts with the column itself. And finally, with ethanol precipitation, again, centrifugation or syringe filters are just not amenable to automation. So a couple years later, we came up with this, which is our PhyPrep system. And this really, we got a lot of support after the acquisition, and Biotage really helped us with engineering support and a lot of support there. So this system is capable of producing 1 milligram of plasmid per sample. The sample is highly supercoiled, which is the form of the DNA that is most likely to result in a successful transient transfection. The sample is endotoxin-free, and because it's part of a system, we get all the benefits of automation. Okay. So we also know that researchers are, that their time is very important, and more importantly, manual steps, if we can eliminate them, then that frees the researcher up to do other things. And we know that there's a quality of life issue when people have to do these manual preps, especially when you're highly educated and can contribute to projects, and you don't need to act just like a pair of hands. And so our big motivation was to attack the hands-on time of a plasmid Maxiprep. So what we wanted to do was just to create something that was very easy to use, kind of a brainless activity, set it up, walk away, and do other things. And so what we did was we used pre-aliquoted buffers. So resuspension, lysis, the precipitation steps are all pre-aliquoted. One would just open the bottle, dump it into the sample, and shake it or invert it to mix. We wanted to use very simple color-coded guides on the bottles as well. The deck then would be set up for 1, 2, 3, or 4 purifications, and we really put a lot of emphasis in it. And Sean really was the driver for this, which was a user interface that was intuitive, easy to use. We know that researchers move around, go from one company to another, and we recognize that expertise can be lost. And so we wanted a UI that can be picked up by new people or by anybody in the lab without having to lose that training. And finally, the sample is collected in a endotoxin-free sterile tube. Okay. Okay. And as I mentioned before, our motivation was to really minimize hands-on time. And so if we look at a PhyPrep Maxi system, if you set up 1, 2, 3, or 4 samples, it takes about 10 minutes, and then one can walk away and do other things. Whereas with the manual kits, it's very obvious that you actually have to attend to the columns, move buffers around, measure out volumetrically the different volumes of buffers. Okay, and we needed to do something that was reproducible. So we had learned that there were attempts to automate Maxipreps in the past by other companies, and there were a lot of attempts at making it a robust system. But it's inherently a difficult procedure, as I highlighted earlier. One can't just take a manual process and automate it. You have to really start over and think about it. And so when we were set out to do this, reproducibility was also a major requirement for the system. And we knew that in the end, what was most important is the yield. So a customer needs to get the yield in order to get that transient transfection, 1 liter culture to get that 1 milligram or 1 gram of antibody at the end. So this is just example data where we purified 4 samples simultaneously, and our goal is to obtain more than 1 milligram of yield consistently. Okay. So we'll move on to now why it works, and we call this dual flow chromatography. So here's a video. So what we're doing is we're actually packing resin. So these are anion exchange resins in a column. These are packed bed columns, and the columns will dip down into the sample and pump that back and forth through. And the idea is that we're really controlling the amount of residence time between the anion exchange resin and the target molecule, which is the DNA. I'll just show this a few times. And the idea is that with every increase in the number of passes that we have, the more likely we'll drive that binding to equilibrium. And that's the hallmark of our PhyTip column, whether it be in the very small scale, where we're packing just 5 microliters of resin, or if it's in this Maxiprep scale, where we're packing milliliters of resin. Okay. So now it's possible for the interactions to be complete, and that allows us to really distinguish ourselves from other technologies. And so just very briefly, we are able to get complete binding. We can get high concentrations of elution by doing this back and forth. We can process different volumes of samples. Our columns here, not just for the plasmid preps, but for protein purification, we can pack any type of column. We can get predictable scale up. And most importantly, this is the format that is most reliable for automation. We call this the PhyTip column, and it uses dual flow chromatography. So if we look at our manual steps and we identify the steps that are most difficult to automate with this dual flow chromatography, with the instrument, and with the design of our column, we've able to eliminate number 2 as a problem, because now we don't necessarily need a completely clear supernatant. We can pump back and forth through and deal with some particulates, and I'll show that later. Our columns are low back pressure, and so that's why we're able to do that. We're able to use packed resins with large bead diameters, and we can decrease back pressure that way. And we're also using wide orifice columns, and that gives us a higher cross-sectional area, which decreases back pressure as well. And so that also clears out number 3. So 2 and 3 are basically related and solved by the PhyPrep column and the system itself. Okay. So we'll move on now to the Maxiprep kit. So this is what the kit looks like. This is typical of a setup where this is one sample. We do have several buffers that are shared that are aliquoted by the customer and put into the system. So the user would get sample filter boxes, PhyTip columns, and tubes, and then also pipette tips. And we have bottles here. Each one are pre-aliquoted with resuspension buffer, lysis buffer, precipitation buffer. We have elution buffer here, and then RNase as well. So the user would first take RNase, add that to resuspension buffer, and then dump that into the sample containing, which would be a pellet of plasmid, a pellet of E. coli. That's resuspended. Lysis buffer is added to that, and that is inverted gently 20 to 30 times. We do have a color indicator dye, so which turns blue when everything's fully mixed. And we give guidelines to ask that one not exceed 5 minutes after the lysis buffer is added. Over lysis will result in a higher amount of single-stranded plasmid, and anything that reduces the amount of supercoiled form of the plasmid will result in decreased efficiency in the transient transfection. Next, the precipitation buffer is added. Again, we are very gentle here, and we invert that 20 to 30 times. The blue indicator dye would then become neutralized and turn clear. And then that is poured into our sample reservoir here, and there will be a filter, and so we are able to do a partial filtration. Some particulates will go through, but those particulates will then not pose any problem with our column. Once that is complete, then the software is operated. It's very user-friendly, very intuitive. These are just screenshots here, so an introduction page, and then one would touch the different buttons. So next, choose Maxiprep. One can select 1, 2, 3, or 4 samples. There are different elution volumes to choose from. We typically recommend using 5 ml elution volume, which would give us the highest amount of yield. If there's a desire to get higher concentrations, we would recommend the 3 ml elution. In some cases, we have been requested to use 2 ml elution, but we find that there is no real advantage in terms of higher concentration result with the 2 ml elution. So typically we'll ask to use 5 or 3 ml elution. After that, there are some checks. We ask the user to look at, to prepare the sample as I described, to load the deck, and then to check the fill levels on the waste carboys. Once those are checked, the system's ready to go, and it will run, and the user is free to walk away and do other tasks. Okay, so the whole chemistry is actually not that novel. We're just taking the chemistry and combining it with a novel form of the separation column. So we're doing typical resuspension with EDTA to reduce the activity of the DNase. RNase is also added to the resuspension buffer, which would remove the RNA from the sample. Lysis is through alkaline lysis with SDS. The SDS will actually denature the DNA into single-stranded DNA. That's followed by the precipitation buffer. So other kits call this the neutralization buffer. Once we decrease the pH back down, the single-stranded DNA will renature. It's easier for plasmid DNA to renature into its normal form. Larger DNA, such as genomic DNA, will then get caught up in the flocculant and precipitate out. This is very typical of a process for removing genomic DNA from a sample. And we are also creating a favorable condition for anion exchange purification. So the pKa of the phosphate groups on DNA allow us to have a pH where we are in a favorable binding situation. Endotoxin removal buffer is used. We are able to consistently achieve less than 0.1 endotoxin units per microgram of DNA. So this is all part of the sample prep. The phytip column is pure, is equilibrated. This is an anion exchange resin, so we're just getting it ready for binding DNA. Wash is a stringent wash where we're going to remove any small DNAs. It'll be stringent enough to remove the endotoxin as well. And then we do elution buffer, and this is actually novel for us. So this is the first anion exchange resin that we were able to screen and find that uses this low salt elution. So we can eliminate the requirement for ethanol precipitation and concentration after this. Okay. So with anion exchange separation, what's tricky is that RNA, DNA, endotoxin basically look the same. They all have these kind of phosphates and with negative charges, and those will bind to the column, which has a positive charge. And so again, what we're doing is we're using RNase to remove RNA, and we use the endotoxin removal buffer to remove endotoxin. So then what's available for binding to the anion exchange resin will be this DNA. Okay. And we worked really hard to be able to achieve this low endotoxin state. And so zero endotoxin is defined as 0.1 EU per microgram. And that's where we are now. There are other kits out there that are automated, and they are only able to achieve low endotoxin, which is defined as less than 10 EU per microgram. So endotoxin are important for transient transfection because the endotoxins will kill the mammalian cells and reduce the efficiency of the production of the protein. And so in our guides and our troubleshooting, if you see very high endotoxin numbers, we can kind of look at different reasons for that. If one forgets to use the endotoxin removal buffer, we're at the 50,000 range. Old cells, especially cells that have been frozen for a long time, we do see an increase in the amount of endotoxins. If the PhyPrep deck workstation is not kept clean from one use after another, we will see higher endotoxin numbers. And technique is actually also rather important when measuring endotoxin using fresh pipette tips and just good laboratory practice will actually eliminate some of these falsely high numbers. Okay. So like I said before, consistency is a major advantage of automation. And so here are just example data for consistency. We get very clean DNA in terms of our A260, A280 ratios, A260, A230 ratios. Our plasmid concentrations are about 250 nanogram per microliter range. We elute in 5 ml. There is some residual fluid that is retained on the column. So these are the yields in terms of volumes that we get, and the yields in terms of actual amount of plasmid. And again, we're very consistent in achieving that low zero endotoxin number. Okay. We do a lot of runs for repetition to get a real accurate number of what to expect, and all of our CV numbers are very good, less than 10. And this goes for yield, concentration, endotoxin levels, and then also the cleanliness ratios. And the DNA are actually very high supercoiled DNA. So what we did was, after doing a typical prep of 4 samples, we compare that to a Kaizen sample. We normalize everything to a certain amount of concentration, and we load the same amount. And the majority of the bands here are the supercoiled form of the DNA. Okay. We are able to accommodate a broad range of input as well. We wanted to have some robustness. A lot of labs, our core labs, and receive samples throughout the organization. And so we wanted to make sure that we knew how to achieve that 1 milligram of yield. And so we can give guidelines and say, if one can grow cells to 5 grams of pellet wet weight, then we are guaranteed to get to that 1 milligram of yield. And so we don't typically like to look at ODs. We feel that there's a lot of dilution factors, and the range of the nanodrops and the different spectrophotometers don't give us a good, accurate correlation between cell density OD readings and the actual cell pellet wet weight. So when possible, we always ask that does the cell pellet wet weight be used as the metric of knowing what is input. So the system can accommodate 3, 4, 5, 6, 7 grams of pellet wet weight and achieve that 1 milligram of yield. So you'll see that as we get cell cultures that are, if there's too much cell input, the unlysed cells actually will decrease the yield. So this won't be a linear relationship or even plateau. There is a happy medium. So we would say 3, 4, 5, 6, or 7 grams is the perfect window for us. Okay. And finally, I'd like to have a note about the salt concentration at the end. So with our system, we're eluting in 50 millimolar tris, pH 8.5, and this is at 500 millimolar sodium chloride. And so if we look at the benchmark Kaizen, that system will elute in 1.25 molar salt. And so because of this situation, the Kaizen kit includes the ethanol precipitation at the end. So because we have 2.5 times less salt than Kaizen, we're skipping that altogether, and we're still able to get good transient transfection from that. So this actually streamlines our process and eliminates that last step that is not friendly to automation, which is the ethanol precipitation part. Okay, and so here are the data to show that. So we compared Kaizen against the Maxiprep from our system, and this is before ethanol precipitation, which was just off the column like I had described. And we also went ahead and split that sample and did ethanol precipitation. And we sent this to Mirus Bio to do transient transfections for us. And these are the percentage of positive GFP that we got from our plasmid. And so as you can see, there really is no advantage to doing ethanol precipitation or not. And we could compare very well against the gold standard, which is Kaizen. This is using transient transfection reagent. Okay, so just a quick note. So for more information, please go to www.phynexis.com/PhyPrep, or contact our sales department with your questions and learn how to send us your cell pellets for a full remote demo.